picking up right where we left off, let's look at that differential equation from the logistic growth model. Again, dp over dp over dt equals kp times the quantity 1 minus p over m. And we notice that that is a separable differential equation. We have a function, your variables here are p and t, and you notice there's no t's at all. So if there's no t's whatsoever, there's no independent variable, then you can think of that as separable. K and m are both constants. So let's go about solving this, and we'll do it in terms of k and m. All right, so just kind of prepare you for what's to come. This is not going to be short. It's going to take a few minutes to solve this differential equation. There's a lot of theory at the beginning of this lecture to set us all up, but it's going to set us up really, really well. And really, in the end, by the time we get to the questions, the vast majority of the work is going to be done for us because we already solved the differential equation coming up right now. Okay, let's go for it. So we want to separate the variables. We want to get all the p's on the left, and we want to get t's on the right. Well, there's no t's, but the dt is there. So let's begin. We're going to divide by p times 1 minus p over m. Notice I leave the k here on the left. I don't need to divide that. I'm just going to divide the p times 1 minus p over m. Okay. Now this doesn't look so pretty, especially when we've got the 1 over. So we're going to do a little bit of algebra on this first to make it look a little bit nicer. Because we're dividing by m here, we're going to multiply top and bottom by m. And it's going to result in what you see right here on the left side. Let me explain. So if we multiply the top by m, obviously that's just m. If we multiply the bottom by m, we can distribute the m inside the parentheses, leaving us with m minus, and it cancels here. So multiplying the m to the bottom, we get p times m minus p. And now we don't have any fractions inside of fractions, so that's nice. Okay, we're ready to go. Let's multiply the dt over to the right and integrate in the same step, like so. As I look at these integrals, the one on the right side doesn't seem to be a problem, a constant dt. But the left side, that looks like it might be challenging. We're integrating with respect to p. The m is a constant. How are we going to do that? This would be a lot more fun if we were all in class together and I could say, what integration technique did we learn in Chapter 7 that we could apply here? And I wouldn't be surprised if some people knew that it's partial fractions. We've got a factor denominator. This is actually pretty easy, partial fractions as far as those go. So let's take a look. M over p times m minus p, well, that's a over p plus b over m minus p. And if we keep going, we can multiply both sides by this denominator here. So we've got a times m minus p plus b times p. And okay, rearranging m, okay, so our coefficients here, the way I solve these, right? So we've got negative a plus b times p, and our constant is a times m, and that will equal the m on the left. Okay, so we can get a system of equations here. Negative a plus b is our p coefficient, but there's no p term over here, so we know negative a plus b equals 0. And a is our coefficient of m, and so we know that a equals 1. And so we can quickly realize, putting the two together, that b also equals 1. So we know the values of a and b right here. And we can move on to writing our left side integral as 1 over p plus 1 over m minus p. dp equals, and we still got integral of k dt right there. This is kind of one of those fun moments, when you're doing math, that you might stop and reflect on your work. And you notice in all the work we've done on this page, There's not very many numbers. There's quite a bit of letters, variables, and different types of variables. Right, as we look back over, right, we see the number 1, and the number 1, and here, A and B both equal 1, and okay, but everything else is a variable. Okay, anyway, just had to point that out. Okay, moving along, let's actually integrate. Let's slide this on up. Well, these aren't too difficult to integrate. You do want to be careful about the second one, though. So we've got the natural log of the absolute value of p. Notice that we need minus natural log absolute value m minus p. Why do we need a minus there? Well, because of the negative p. If we were to perform a chain rule here, we would then have to multiply by the derivative of the m minus p, which is a negative 1, to turn that back into a positive. Be careful about that. Okay, it equals, and here on the right side, well, no big deal, constant, right? So kt plus c, we get that arbitrary constant there on the right. Okay, where to go from here? We are going to find an explicit solution. There's no stopping us. We're going to be able to take it all the way to an explicit. We're going to solve for p. I think I continue on the next page. So let's put that right up here. That's where we are. Okay. What can we do? Let's begin by combining those natural logs. So natural log p over m minus p, and we got that same right side. Okay. Once we have those combined, now we can apply an e to both to cancel out our natural log. So on the left, we've got p over m minus p, and on the right side, e raised to kt plus c. One big thing to point out that a lot of students miss or have trouble with, we need to apply e to the entire right side. So this entire thing goes into the exponent. E raised to the left, e raised to the right. We don't have the plus c just sticking off on its own. It's part of the right side, so it has to go up in that exponent. And we arrive at this. Now, speaking about the plus c, there's some pretty nifty simplification we can do here, since c is just an arbitrary number. Check this out. This is some magic. Think of the right side as e to the kt times e to the c. Right, that would be true, right? Because if you were to multiply these, you would end up adding the exponents. Okay, so those are equal. Hey, if c is an arbitrary constant and e is another constant, isn't e to the c just itself another constant? So here's what we're going to do. We're going to say, let's rewrite the right side. Let's just think of that whole thing as a c. So we got c times e to the kt. Woohoo! That's pretty cool. All right, and the whole thing, of course, p over m minus p equals c times e to the kt. So we're kind of simplifying things as we go, because we want our solution to this differential equation to look as neat and tidy as possible. That's going to be big. So tricks like that are essential in differential equations. It's not optional. Okay, what to do from here? If we want to solve for p, there's a few ways we could go, but one way that is maybe not an obvious one, we could take the reciprocal of both sides, and we'll kind of get to the reasons why. It would be a lot better if this was flipped over for our algebra's sake. So we're going to do that. We're going to take the reciprocal of the left side, which means we need the reciprocal of the right side. So let's do it. Well, let's talk about the reciprocal of the e portion. The reciprocal, we can just throw a negative on the kt, and that's the reciprocal. And notice the c remains. Why is that? Because the reciprocal of a constant is just another constant. Oh my goodness. So we are taking the reciprocal of the c, It's just another constant. Sometimes you'll see people, you kind of look at what we've got here, this C to this C to this C. So these C's, we just want to be clear, these C's are not the same number every time. Sometimes you'll see people write C1 and then maybe here write C2 and C3, indicating that it's changing every time. If you really want, you can do that. In the end, we just want an arbitrary constant in our solution. So that's really not necessary for what we're doing. Oh, but we do want to recognize these are not the same C value each time. Okay, so what's the point of this reciprocal? Let's split that fraction. Okay, so I'm going to think of it as m over p minus p over p, which of course is 1, equals that right side. We're going to go ahead and add the 1 over. Now when we do it, we're putting it to the front. That is the convention in a case like this for the logistic growth model. Let's think of it as 1 plus c e to the negative kt. And on the left side, of course, m over p. Now, if we want to solve for p, what can we do? Well, turns out we want to do the reciprocal again. Flip this back over, and we're almost there. We're almost there. Okay, so another reciprocal will be p over m. And notice now on the right side, because of this addition, there's no clever, sneaky way to do it. We simply have to write this as 1 over 1 plus c e to the negative kt. And we're almost there. All we got to do is multiply the m over at this point. And we found an explicit solution. The population size p equals m, remember that's your carrying capacity, over 1 plus c e to the negative kt. That is impressive. And now that this has been done for us, we don't have to repeat all of those steps when we do problems in the homework or quizzes or tests, because it's already been done in general. This is like a new formula that we have, the solution to the logistic growth model. Turns out we don't want to stop here though. There's more to do. We know m is the carrying capacity. That would be told to us in a problem. The same with k. K would have to be told to us in a problem, or at least we'd have enough information to figure it out. The c is another story. Turns out we can treat this like an initial value problem. We can find the value of c. How are we going to do that, you ask? Okay, let's go there. The initial condition is time 0. The population is p sub 0, or sometimes you hear it called p naught. At time 0, you have some initial population size, right? So let's just call that p naught, and that would be given to us in a problem as well. What's the initial population? Okay, so thinking of this as our initial condition, let's figure out what c is. And then all the pieces of the puzzle will be there. All right, so what we'll do is we'll plug in our initial population for p, so we're going to call it p naught, and we plug in 0 for time, right there. And we're going to figure out c in terms of the other parts. Okay. Let's see how this plays out. Well, because we're raising to the 0 power, that really makes life a lot nicer for us. E to the 0 is 1, of course. So this breaks down to p naught equals m over 1 plus c. And it won't be too hard to solve for c at this point. All right, we can multiply the 1 plus c over here, divide by the p naught, and then subtract 1. It turns out that arbitrary constant c will always be your carrying capacity divided by your initial population minus 1. That's just the way the formula would have to fit together. Okay. Now we're going to put all these pieces in one statement so we can see it all in one place. That will be really nice. Here's the logistic growth model in its full glory. The logistic growth model is modeled by this differential equation. That's where we begin. We realize that the rate of change of the population size, dp over dt, equals k times p times the quantity 1 minus p over m. And we'll note the initial population is p naught. So this is where our logic started, and we realized, okay, well, if that's a better model for population size, well, what would be the solution? And so we can solve that differential equation. It has solution p equals m over 1 plus c e to the negative kt, where c equals m over p naught minus 1. And so if all we know is the carrying capacity and the initial population, then we can put, and the k would be told to us, we can put that all together. And with this, I mean, what is this really? What is the solution? We can figure out the population size at any given time. If we can fill in all those parts, tell me a time, I'll tell you the population size. That's what we're going to do in the examples in the next video.